book, so we have some
copies of the old version.
Yeah. So if you want to take
to check a few things. Otherwise, you can download it from internet. There's a link. I'll show you. So yeah, I mentioned a few things about the waves, and we introduced the spectrum. And what I want to say now, before I finish on this, is that the spectrum actually changes in space and time. So the spectrum really represents the sea state, or rather, we represent the sea state of all the properties of the waves are represented by the spectrum. And this corresponds to a stationary and homogeneous sea state, if you want. So ideally, you could reconstruct something that looks like the waves from these statistical properties. And that would make sense if the waves do not change in space and time. Of course, the waves change. The wind blows, the waves grow, they go to the coast, they break, and things like that. So there is also an evolution of the sea state. And so these spectra actually also evolve in space and time. And so these properties of the waves will change in space and time. And I will just say a few things about that before I go into more details next week. Just so that everybody is on the same page. So there's three things I want to talk about. The fact that the waves propagate, okay? So the wave crest moves and the energy moves with the waves. The waves refract, so they turn, and what we call shoaling, the fact that the waves energy gets focused because the waves slow down, and so locally the wave energy goes up. So as I said before, we have energy, and we have a propagation of the energy with the group speed, which I write as Cg. In the presence of current, you could say that the group speed is changed. Another way to write things is that you have an advection of the energy which is done at the speed which is a group speed we had before plus the current. And I will not discuss here the details of is it the surface current, the depth average current, or some profile of the current. Actually, each component of the spectrum feels a little bit different current, and this, when people look at HF radar, the HF radar is sensitive to given wavelengths of the surface because of the backscatter of the radar. But just to make it simple, if the current is uniform of the depths, all the waves are advected by the same current. If not, then yes, there's a difference between short waves and long waves. So the velocity, the energy goes with the group speed plus the current, and this sum is actually the vector sum. You could have a group speed one way and the current the other way, and then the wave would just propagate one way and being moved by the current in the other way. And this is just some example of how to visualize things. So in that case, there's no current. So the waves are the group speed and the phase speed are a function of the water depths. And in that case, what's happening is that we have the same wave period, and so the waves go from deep water to shallow water, and as the depth changes, at some point the crest of the wave will turn. I think I had some nice cartoon of that, but no. So basically the waves go faster in deep water and slower in shallow water. And that means that as you go over the edge of this, here the submarine canyon, which is deep in the middle of the canyon, it's shallow on the side. And so the waves that go along the canyon wall, the crest, in the side of the crest which is in the canyon will travel faster, and here it's going slower. And this is why you see the front of the waves is taking this shape. With this part is going faster, and that part is going slower. And as a result, then the wave just turns, and you can see if you follow a trajectory of the wave, it's called a wave ray, like light rays, and the ray will just turn, and the energy just goes like that. Because here it's going faster, and here it's going slower, so it's just turning. So that's an extreme case or submarine canyon, but any topography near the coast will do the same. And typically, if you have a shoal, a shallow water region, like you have here between the two canyons, this shallow water region is like a lens in optic. You have a converging lens. The light goes slower in the glass compared to the air, and so the light ray will bend. And so this region with shallow water is essentially focusing the energy of the waves in this part of the beach. And this is actually, people go surfing. So Scripps is somewhere around here, I believe. And so there's a nice black beach spot for surfing just north of Scripps. Yeah, this is from California. You have San Diego around here on the bottom of the page. You see La Jolla, and Scripps is right there. And so there's this place has been studied a lot because there's a lot of oceanographers working there. And so we had an experiment, 2003, with a lot of buoys in this area. And if you make a map of the wave height, so this is just a surface elevation with low values negative in purple and high values positive in red. And so you can see the crest one by one. And the wave height with just an average in time of this. And you see that you have a tongue of high wave heights between the two canyons and lower wave heights at the head of the canyon. So that's effect of refraction. Geez, I have some ice here. I don't know what I want to say about the ice, but I'll think about it. That's a case in which we do some modeling of waves going. So this is Norway, Greenland. The ice edge is the blue thin line, and the color is the wave heights. This is swell coming from the storm. So this is a snapshot. At one point there was swell here, and another swell here, close to the North Pole, and there was a measurement station close to the ship, which was stuck in the ice. And this is a measurement at the ship. Actually, it's instruments put on the ice close to the ship. And what you see is the evolution of energy in the log scale as a function of time and frequency. And so the frequencies, I don't have it, but I have the periods here, so 33 seconds to 14 seconds. So these are really long swells. You have two events, which I call swell 1 and swell 2, between February 12 and February 14. And so swell 1, and this snapshot corresponds to this time when the swell 1 is coming from a storm. So the storm was here, and the swell traveled thousands of kilometers across North Atlantic and into the ice. And so we have, yes, this kind of propagation also under the ice. And typically, because the phase speed can change also due to ice properties, in general, you may also have some refraction at the ice edge. Although there is actually very little evidence of that, because at the ice edge, the ice usually is broken up by the waves, and so the phase speed doesn't change so dramatically. Yes, so the waves turn. So they turn, as I told you, due to changes in water depths, in shallow water and deep water. And if you plot the sphere on the map, this would be the trajectories of the waves. If you imagine waves that arrived in California and you're trying to look where they were a few days before, so this is 15-second waves. So the first circle here in green is 1 day, then 2 days, 3 days, 4 days, and so all the way to Madagascar it takes 2 weeks. So you can play this kind of game and compute the trajectory of the waves. And on this map, it looks like the waves turn, but actually they go straight on the sphere, right? So they just follow the great circle routes along the Earth, like an airplane traveling from one place to another. If you go straight on the sphere, it makes a curve on this projection. And so in the numerical models, we actually have a term in our equation to turn the waves, but that's just because we have some reference direction, which is usually the North Pole. But in practice, it's a straight line on the sphere, so it's just turning on the projection map. Oh yes, this I already told you. Refraction due to shallow and deep water. That's another example of the Los Angeles harbor. And effect of the currents, which is a local example here. So these plots show you some time series of wave heights. As for times, it's the months of October, November, 10 years ago. And what we had was measurements of the wave height in black, and the measurements coming from a buoy which is located here. So you have the west of France here in Brittany. We are right now right there. We have some island here, and there's some currents. And so we put the buoy there 10 years ago. It was a nice place because there was no fishing there. And then we looked at the data, and there was all these jump up and down of the wave height. And so some people doing coastal work here were complaining, you just put the buoy in the wrong place. Well, I thought it was interesting. And so the question was, so why do we get this wave height going up and down? Well, the reason is that we have currents around the islands. And at low tide, the current is going this way, and the waves go when they go opposite to the current, they get refracted. So the colors here show you the currents on the bottom left plot, and the rays here, these lines are the trajectories followed by the waves. And what you can see is, at that case, the waves go away from the buoy, and so this is why we have a low value of the wave height during that phase of the tide. When the tide reverses, we actually get bigger waves at the buoy. So waves also turn due to currents, and the radius of curvature of the rays, so you can fit a circle to the shape of that ray here, is given by the ratio of the gradient of the current, which we call the vorticity, and the group speed of the waves. And so if you have a strong gradient of the current, you get a small turning radius, so the waves turn faster. And if you have waves that are slower, with a slower group speed, they also turn faster. And that gives you some maps of wave heights like that from the model. And finally, the last thing I want to talk about is the wave shoal. And what we mean by shoaling is that the wave height changes to conserve. So in the absence of current, we're conserving the energy flux. And because the group speed changes from here to there, you have shallow water, so group spinning is less than the deep water in general. The conservation of energy flux means that you will have more energy per unit surface here, which means you have higher waves. And this is very much, imagine cars on a highway, and so there's a traffic jam. So the cars slow down in the traffic jam, and the equivalent of the energy is the number of cars per unit surface. So usually the number of cars is conserved. And so because cars slow down, you have more, it's more packed, and so you have more number of cars locally, just because they have waves coming in here, so cars coming here, and they're slowing down, so you have this convergence of the energy flux. In the presence of currents, the energy flux is not conserved anymore, because wave exchange their energy with the current. So the current can take wave energy and vice versa. And so instead of the energy, in that case, we'll work with what's called the action. And the action, for making things simple, and I'm looking for an eraser, I put it here. The wave action is, to make things simple, it's a bit more complex than that, but basically it is the energy divided by the intrinsic frequency sigma. And this sigma changes as the wave propagates over the current, and so this is a thing that will be conserved, and so what will be conserved then is a group speed times the action plus the current. So we have a flux of action that will be conserved when we have also currents in this plot. So this, yes. And so when we look at maps of currents and then maps of wave heights, so that will be the map of wave height without the current, that's the map of wave height with the current, and you can see that the current gradients introduce some gradients in wave heights, which is mostly due to refraction, but also due a little bit to this shoaling effect. And this is a picture from south of, this is a Drake Passage between Antarctica and Chile here. But you get the same kind of map everywhere where you have currents. And finally, going all the way to the beach, at some point the wave will break, so there's some wave breaking in deep water. There's also obviously some breaking at the beach, and these are some observations of waves going over the beach. The depth goes from 5 meters here at the outer edge of this computation domain to something like 2 meters here, and there's no sensors there, but what you see is that you have a curve of wave heights as a function of time this time, in hours. So it is in deep water, and as you go from deep water to shallow water, you can see the wave height shrinks, and you can start to see a very strong control of the wave heights due to the water depth, which is coming from the tide. So at high tide, you get bigger waves, and low tide, you get lower waves, because the maximum wave height is limited by the water depth. And typically, the ratio of the wave height to the water depth is maximum of the order of 1/2. So that's all I want to say about CSAT in general. So we have a wave spectra that represents the distribution of the wave energy. Because of this action thing, we also will be talking about action spectra, not just wave spectra, but for measurements it's actually more practical to work with the energy spectrum. The wave height is defined from the standard deviation of sea surface as 4 times square root of the variance of the surface elevation, and this variance is just the sum of the entire spectrum. And this wave spectrum changes in space and time due to various processes, and we'll discuss that more tomorrow and next week. That's wind generation, wave breaking, effect of ice, and other things, wave current interactions. And that's it. So if you have any questions about C-state in general, that's the time. Okay. Hopefully, it's nothing much new in here.